So thanks for joining us this afternoon. My name is Gerald Matarazzo. I'm a 3D printing application engineer here with Fisher Unitech, and this is a brief webinar on DFAM, or Design for Additive Manufacturing, specifically for FDM. So we have a couple things we want to talk about today. So quick overview of who and what Fisher Unitech is, as well as a quick overview of myself. I split this conversation into some FDM basics, as well as some FDM intermediate information, a little bit of information on special materials we have out, nylon carbon fiber filled, as well as TPU, and then some more information on generative design, as well as post-printing considerations, which we'll get to at the end, and then finally Q&A for anyone that might have questions, comments, concerns on what we're talking about today. So, quick rundown on Fisher Unitech. We are one of the top VARs in the country for Stratasys product, as well as SolidWorks and Desktop Metal. We do have some other product lines here, but basically we can help you from start to part with anything having to do with 3D printing or advanced manufacturing. Quick rundown of some of our partners: SolidWorks for CAD, Artec for 3D scanning, Stratasys for FDM and PolyJet as well, Desktop Metal for bound metal deposition, which is essentially a metal FDM version of 3D printing, as well as Nanodimension, which prints multi-layered PCB boards, and finally post-process, which has automated support removal as well as automated surface smoothing technology available. A little bit about me. I am a certified 3D printing application engineer for all of these product lines. I'm also a certified project manager and a certified lead Six Sigma Green Belt. We actually did a talk and webinar a couple months ago on optimizing additive manufacturing with Six Sigma initiatives and processes. So if you want to learn more about that, feel free to contact us and we can send you that video over as well. So FDM stands for Fused Deposition Modeling. It's essentially that hot glue gun technology you see pretty much everywhere. It's the most common and popular 3D printing technology that's out there. It's also the highest customization in the industry, meaning you can literally customize a part down to the individual layers. And those layers can be anywhere from 13 thou of thickness down to 5 thou thickness. So there's a lot of variety and customization that you have in front of you with certain software and material. If you don't know already, this is kind of a basic setup for an FDM machine right here. On the left-hand side, you'll see two different extruder nozzles. So one was for the model, one is for the support. And these extrude out these materials in tandem to generate a part, which then can either have that support structure broken off of it or eroded away in a soluble bath. And then we have thermoplastics that are extruded on these FDM systems, ranging from your standard ABS all the way up to high-grade aerospace certified materials. And then some quick terminology: outer layers of a FDM part are called contours, inner layers are called rasters, and you'll see what that means in a few moments. So with DFAM, again, Design for Additive Manufacturing, you want to have a framework in mind with designing these parts. A lot of the time you'll see very seasoned, very experienced individuals in the design world and the manufacturing world. They're really good at designing things for the constraints of the processes that they're used to. The wrench, so to speak, that 3D printing and FDM brings into any manufacturing environment is the high complexity and some of this design freedom that you'll see with some of the highly complex parts that you'll be looking at soon. So some things to keep in mind is the design freedom, which basically means high complexity and little to no limitations that you see with traditional CNC. Orientation is a huge factor when it comes to design for additive manufacturing. You get the exact same part, but depending on how you orient it, you could have completely different strengths, aesthetics, and so on. Print scope, so figuring out what size you want to print of these parts, how much of a volume you're looking at for these types of 3D prints, as well as the size of a print based on what your build volume is or what your build plate is. These are all things that we could talk about a little bit later. One of my favorites is hybrid fabrication. So there's a misconception that 3D printing is taking over or surpassing CNC. It's not that at all. It's actually complementary to CNC. Quick example is if you want to have a very thin plate created, chances are CNC makes more sense for those flatter parts, and 3D printing makes more sense for the higher complexity models that you'll see. Material considerations, so just basically figuring out what material is appropriate for the right application. So do you need chemical resistance? Do you need high strength? Do you need it to be ISO certified? Things like that. And then lastly is part interior considerations. So different part densities, sticking material around the holes, and all of these different interesting settings that you have available to you to completely rework and customize the innards of every part that you build. So some FDM basics, and we're going to start with orientation here. Critical success factors are huge with orientation. Orientation is basically the very first step you take at building a part, and it's going to have a significant effect on how that part comes out. And there's usually a trade-off, not always, between function, aesthetics, print speed, and material consumption. Sometimes you get 2 out of 3, maybe even 4 out of 4, depending on what kind of part you're looking at and how you're orienting it. But there is sometimes a trade-off, and that's what you have to figure out before you even start. Which factor is the most important to you? Does it need to function perfectly? Or maybe does it just have to look nice for a marketing event? These are things you need to think about before you even start printing. Some examples here of orientation of the same part. So on the top left, you see one orientation on its side for strength, because the force always wants to be perpendicular to the layers. And I'll show you a better example of that in a few moments. Right underneath that is the same part laid flat. So the flatter the part, or the lower the Z imprint is of that part, the faster it's going to print, simply because there's less layers to print. And then for aesthetics on the right-hand side, you're seeing this part standing up. That is for the best aesthetics, because you're looking for the shallowest sloping, or the least amount of sloping or stepping possible, because it'll make those layer lines less prominent to the naked eye, which means the part is just going to look nicer, i.e. a better resolution. And then another quick example and a visual for layer adhesion as well as orientation. If you take a look at these parts, it's the exact same part, but printed in 2 different orientations, and you could see how those layers intersect one another and would be able to resist certain forces. The part on the right-hand side is going to be much stronger than the part on the left-hand side, simply because of the way that those layers are deposited. A good way to think of it is a bundle of sticks. So as long as you have layer lines that are perpendicular to the forces that are going to be acted upon that part, you should be good to go, depending on how thick and how solid you make that part. And then there's some really easy redesign work that you can do. This is stuff you can do in minutes within SolidWorks. If you have a lot of these types of sharp overhangs that you see on the left-hand side, chances are that's not a complete requirement for that build. It's just the type of geometry that your shop might be used to because of CNC work. So all you need to do is put some fillets in there and chamfers to get to a 45-degree or so angle, which will make those geometries self-supporting and therefore will require no support at all. So there's no support to take out, and the print will actually move faster because there's less deposit. And a good thing to think about is curves are free with additive manufacturing. So any of those things that you normally have to machine, all you have to do is click fillet or chamfer in SolidWorks, and it just does it automatically for no additional tooling cost. Okay, some talking points on infill. So here are some of the basic infills you'll see with any FDM machine and any FDM material. So going left to right, solid, pretty self-explanatory, as dense as you can get it with basic parameters. Sparse high density, then sparse low density, and sparse double dense. So it really depends on how sparse you want to make that part for a reason. Again, if it's a marketing part that you just need cheap and quick, making it more sparse makes more sense. Maybe it's a part that needs to be really strong, so maybe you'll make it solid. It really depends, and it's a case-by-case example, which is the whole point of 3D printing, having that ability to reiterate so quickly. Now, if you get into what's called Insight, our Insight processing software that you see with the Stratasys F370 machine and higher, that is where you have some really complex settings that you can spend hours and hours on figuring out how to work. Essentially, what you see here is editing anywhere from how many outside layers or contours you'll have for each individual layer. So you could thicken up areas around a hole to make sure that they're better for drilling and tapping, which we'll talk about a little bit later. Maybe you want to edit the air gaps between different contours and rasters, or contours and contours, which basically means those layer lines will be tightened up a little bit, making that part even more solid than the typical 80% you see with the standard. Or you could make it completely opposite and do very particular, very alternative fill patterns like sawtooths and things like that for whatever the application might be. So you can spend a lot of time working on this. And in Insight, you have both general toolpath parameters that you see on the left-hand side, which kind of will be enacted for the entirety of the part. But you also have custom groups on the right-hand side, which allows you to specifically choose certain curves and layers of that part to edit it specifically for these different things. So you could have, like I said earlier, layers that are completely processed separately for whatever the issue orientation or feature is on a certain portion of that part. Another thing to look at with contours is you can do some basic modeling and dimensioning in SolidWorks again, and do the math to figure out what contours make the most sense to have parts like you see on the right-hand side here or on the left-hand side. So very fine feature, very high resolution, simply because you're optimizing the ability to print one contour, one single layer at a time for the application. You can see the similar type of application for living hinges. Essentially, you'll be able to deposit several layers down flat, which will create a hinge in of itself. And then one other tool that is useful to talk about within Insight is a stabilizer wall. This is a quick tool that you can put together in a few seconds or minutes, depending on what you're working on. This is for parts that are very tall and very thin, or either or. And if it's a part that you need to have printed that has that kind of issue, if you don't have a stabilizer wall, you might see some warping or curling because as that part grows and gets taller and taller, it has a greater chance to topple over. So something like a stabilizer wall, like you see in front of you, is simply a literal wall that you can construct on the side of the part to kind of give it a backbone as it prints. And you could even choose the contact intervals, meaning how often it intersects that part. So basically, you can tell it, okay, I only want this stabilizer wall to touch every 10th layer, 20th layer, 100th layer to minimize the damage to the aesthetics that will happen to that side of the part. Support. So one quick thing, or one of the most important things about support is normally holes. Holes are usually a very big concern when first getting into 3D printing, especially the horizontal ones. Because if you look here, if we printed this rectangle as is, you would have a lot of stepping on the inside and then have this entire cylinder here caked in with support. So a way to get around that is maybe undersizing them and making them in a diamond shape. So minimize the amount of support because there's now 45-degree angles that act as a both a reaming guide as well as a self-supporting angle, or a teardrop shape that you see on the right-hand side, which is also very good for eliminating support because, again, there's no overhangs anymore because of that 45-degree angle you just created. And I already said this a couple of times, but 45-degree angles do not require support. So whenever you have an opportunity to slightly adjust your geometry to go from any other degree other than 45, you always want to switch it over because it'll allow you to remove supports. That means faster print times and cheaper parts and less to clean up. So your throughput for batches of prints, not just one individual print, will go much, much faster. And speaking of batching and moving faster, there's also consolidation to consider with 3D printing. Being able to create assemblies all in one right off the printer is huge. So any type of hinge from ball, pin, dimple, living. You can also make chains or maybe a telescoping pattern to be able to print all of that in one go based on the different tolerances you might want to give a part to make sure that it has the appropriate clearance to free itself once you put it through a support bath. And here's a quick chart as reference to kind of give you an idea of the types of layer thicknesses and the corresponding toolpath widths, as well as the clearance that you would need to give certain parts to be able to have these types of consolidated assemblies. So it's a really big deal because it's less to print and it's less to post-process afterwards to get the final product, which would be that chain, that telescopic part, that hinge, whatever it might be. Pauses and inserts is another interesting topic. So again, in Insight software, you could actually design your part to stop printing in certain areas for different reasons. Maybe you want to put a cavity in there and have a pause to physically put in a metal insert or maybe a magnetic insert, and then have the print continue on and actually cover that, encasing that insert within the 3D print itself. So not having to press fit or anything like that is pretty interesting. Or just to simply swap out material colors and have a multicolored part for every reason, maybe for indication or water levels, things like that. You'll see examples of. And then just here's another particular viewpoint of an insert on that snap that we were looking at earlier. The red arrow on the left-hand side here shows the gap that was created or the cavity that was created to have that insert put in halfway or partway through the printing process. And you could do that while having that pause work there, or you could just design a cavity in and of itself to press fit later, which we'll talk about. Now, going into the specialized materials, we're going to start with nylon CF, or nylon carbon fiber filled. This has been out for a little while, and it's a pretty popular material, so if you know anything about Stratasys, you've probably heard of this already. It's one of the harder materials to print with, which is why I chose to put it in this presentation here, because if there's any current Stratasys customers, this might be something that you're interested in. On the left-hand side, you can see default settings that the material is originally released with. So because it's such a difficult material to print because of the carbon fiber within it, you usually see a lot of air gaps, and the part resolution doesn't come out too great. Well, looking at the enhanced surface that we've been able to develop, and even a further modified enhanced surface, you can completely change the aesthetics of that part and actually make it more sealed as well as stronger because there's less air gaps between those layer lines, making it a more truly solid part. And just as a quick reference, if you want to know the type of strength you can see with nylon CF compared to our original nylon 12 or our very high-end aerospace Ultra material, you kind of see the two important metrics at the bottom here, tensile modulus and tensile strength as a comparison. And another innovation that we've been able to create within the Insight software itself is being able to add extra contours and tighten that all up around bosses or holes, again for tapping, reaming, things we'll talk about in a few moments here. So again, just some very specific tips and tricks for anyone that is interested in nylon CF perhaps, or is currently using nylon CF, because I know that we have a smattering of different people on this call today. And then some more quick information that you could jot down or get after this recording is sent out to all of you is some more information on tool paths as well as infill settings. So with nylon CF in particular, the sawtooth pattern has proved to be a better structural fit and a good replacement for sparse double dense, basically the middle ground between completely sparse and completely solid, which was previously unavailable with this material. So now you're able to get the type of dual benefit of a sparser part with the strength of the material in nylon CF, which we didn't see previously. So it's a really great innovation. So both with improved aesthetics as well as improved strength and structural capabilities with this material has been a really nice breakthrough the past few months. TPU is what I'm most excited about recently. This is a brand new material, and it's kind of a brand new territory for Stratasys. So TPU is an elastomer material that has come out for the F series machines. So being able to print out hoses, tubes, air ducts, basically anything that needs to be used as a cover or a seal or something with a good amount of toughness that can be used to protect something. There's a lot of value here in this material. So very high elongation to break, very good toughness. The tear resistance, I haven't seen anything even remotely close to it yet, and also abrasion resistance. So again, caps, seals, things like that, this material is really good for. And you can see the elongation of break and the elongation of yield is off the charts. Again, I haven't seen anything really close to this even on the polyjet side, which typically has better rubber-like materials. So this is a material that you might want to look deeper into, especially if you currently have or are considering an F-series machine. It's going to be something that you'll find a lot of applications for around your shop. So, and then some quick information on this elastomer. It only prints in 10 thou, which is actually good. You want thicker layers for this because of the adhesion. It doesn't function as a typical FDM material, meaning the type of conversation we had earlier with surface area and layer adhesion. It doesn't apply the same way to TPU because it's an elastomer. So you could have very minimal surface contact between layers, and it will still have that really nice toughness and really high elongation to break. just because of the nature of the material. It's not like a thermoplastic. Some other talking points is instead of a 45-degree self-supporting angle, it's now a 55-degree because of the complexity of the material. And you're going to want to keep these parts as low in the Z as possible, just because it gets a little trickier to print out this gummier material as you get a taller and taller part. And then most of the time you want to leave it in the high dense setting that it comes in with, just because you want parts like this more dense as opposed to hollow, because the whole point of it is to be a rubber-like material. Another interesting field that we've come across recently is called generative design. So you might have seen different versions of this in the field already. We're going to talk about one in particular. But before we go into that, the current design process, you want to have that in mind when talking about generative design, because it's flipping this process entirely on its head, going from the typical bar napkin sketch, the 2D sketch, then making those sketches and importing them into a CAD program, extruding those 2D sketches into a 3D model, and then after a lot of work and legwork and maybe some post-processing, you eventually get a 3D print that might be a little more optimized for strength to weight as opposed to what was designed originally. But the whole thing to think about is whatever you're designing yourself, you need to realize or consider if you need all of that material or even all of the features of that geometry to get the function that you need. Again, with 3D printing, you always want to focus on the function of the constraints of what you are previously used to with, say, CNC, injection molding, whatever. You always want to try to base your print around the function that you're trying to get out of that geometry. So what you're kind of seeing right now, this is just a very long-winded description of what generative design is, but the basics are you choose a build area that you want with a couple constraints. So maybe a certain O-ring or a certain bar or a certain surface that needs to be a certain size and thickness. And then you tell the software exactly what the parameters are. So the forces that are acting upon the material that you're building this part in, and essentially you start getting a part that starts to come into form based on those constraints by literally growing a new geometry within those confines. So the constraints, those cylinders here that needed to have touch points, and then the rest of the area here is the build constraint, i.e. what the part used to look like when it was designed by humans. When you use generative design, it's able to cut away or trim all that fat away to get to the geometry that you only really truly need to get away with, to get the result that you want. And you have something like this. So again, pay attention to what the design used to look like when it was originally designed by the human designer, and then how much you're able to shave off by having this optimized strength-to-weight ratio with this generative design software. It's something to really think about, and then whatever you're paying, or saving rather, with this generative design software program optimizing your parts, multiply that by however many parts you're making of that typical geometry, that standard geometry, and then think about all the other parts or dollars you could save on all the other parts that you're printing or looking to print in the future. And this is a software that's out right now. So this is called Desktop Metal Live Parts. So you could actually download this for free right now and start doing this yourself if you wanted to start playing around with the software that can optimize parts for you. So something to think about. And then questions to ask about this is, like I said earlier, how much time did you save with designing, printing? The biggest thing here is how much material and therefore how much cost did you save per part or per batch? And could you even do this without 3D printing? The short answer is no. And another great thing about the design or the generative design software that's offered by Desktop Metal, again called Live Parts, is you can export this new generatively designed file as an STL and print it out on any machine. And we have an example here that one of our other coworkers within Fisher Unitech, my colleague Simon out of Philadelphia, he's another certified 3D printing application engineer, and he kind of gave this Desktop Metal Live Parts software test run. You can see the constraints that he put in for these parts here, and then the build area that he allowed the part to develop within. And then he just made that in solid PLA, barely a cubic inch, and it was able to take a 50-pound load and a little bit more. So you kind of get a feel of what it looks like, and that's off-the-shelf consumer-level PLA. So you can think about the kind of geometries that this can support with high-level materials, PC, PCABS, Ultim, nylon carbon fiber filled metals, you name it. Post-processing is another interesting way that you can consider right from the design stage of how you want to get that function, that end result. You can combine the value of post-processing techniques with the design considerations you'll make in the very first stage of product development. So I'll show you what I mean. So if you want to have a very precise thread or tap a hole, anything like that, it might just make more sense to design in your software on your part just to thicken up that hole where you would want that thread to be instead of trying to just have the 3D printer try to get the same accuracy that you would want off a metal machine or off of a CNC machine. It's not going to get there. So your best bet is to simply thicken up the area around that hole by simply adding more contours around it, which will allow your reaming or tapping to cut into those extra contours, making that thread, as opposed to banging into these rasters here, which would not make for a good thread because you would have all those gaps. And then also to consider the cost savings of being able to just print the same exact part in FDM and then still getting the same machined quality accuracy of that reamed or tapped thread. And then some other types of post-printing techniques you have here, a couple different versions of inserts. So being able to press fit in bushings where, for example, hot or abrasive materials would touch. So being able to have 90% or whatever percentage of that part in your lower cost thermoplastic, then having the high contact area points just in a metal that you're able to press fit in there. These bushings as an example. If you don't want to tap or ream or drill or whatever you want to call it, those types of holes where you want to insert a threading, you could simply put a heat insert in there. So having a type of brass insert for this, in this example right here, then heating it up and using a press fit system to just push it in there. And then another interesting example here is location features. So being able to design stuff like this and put in magnets. So on the opposite end of that part, you can find the magnet based off of the magnetic pole that will be able to come through the FDM part. So if you need to use magnets for placing or spacing, whatever it might be, this is a very quick way of doing that without having to go and machine a big chunk of this part or the entire part to compensate for those magnetics or rods or anything else. Another thing to think about is sectioning. So sometimes, again, we talked about orientation a few times today, you might not be able to get all of the critical surfaces out with one orientation. And that's going to be problematic for this part right here. So a way to get around that is to simply section off these parts and assemble them afterwards. So we'll do dovetails, pins, cavities, bonding, gluing, you name it, or even a snap fit perhaps, to get all of the critical surfaces out the way you want them to. So it's a really simple way of preserving all of the critical success factors, defined features of a more complex part without having to machine it or being able to not even achieve it at all off of 3D printing. This is something to really consider. And also, depending on the size of your part, you might have parts that are too big for your build chamber. All you have to do is print it out in sections and then design dovetails into them or bond and glue them or simple pins and cavities or snap fits, whatever you want to do. Now, with post-process technologies and other types of tumblers or media blasters, there's a really nice trick to get the value and cost savings of a very low resolution print and a very sparse print and still get a great surface quality. So here's a quick part that I made a couple months ago. This was in the sparsest setting possible in the lowest resolution, meaning it was the cheapest way I could have possibly made this part and the fastest way I could have printed this part. But I was still able to get a roughness average or RA value similar to injection molding by just using those lower level settings and then throwing into a tumbling machine provided to us by post-process. So it's really great for having very fast throughput for prototyping, marking, what have you, because you're able to optimize and capitalize on very quick and dirty prints and smooth them out in a post-processing technique. Again, media blasting, tumbling, whatever it might be. So I know that was a lot of information, but we wanted to try to put as much value into this presentation as possible and spark some interest or kind of give everyone on the call a broad understanding or perspective perhaps on what's out there right now. And this is just the tip of the iceberg. So at this point, we like to invite you to ask us questions or leave any comments or concerns about some things you heard from me today. And again, if you have any interest or information, reach out to me. Go onto the Fishing Tech website. We have plenty of content on there. But yeah, at this point, I'll let anyone that's out there in the audience speak up and pick my brain or my team's brain.